Hello everyone, welcome to another stream. How are we doing? Hey there, Krez, welcome. Can you combine Froxels with a BVH? Well, that we're not like directly, but they'll probably they'll probably they won't work with each other. They'll just work on different aspects of in the rendering, I think. Yeah. So last stream we did some optimizations. And I think I've disabled it now. Okay, this is the tiled renderer, whoops. Yeah, last stream we did some optimizations and made the BVH traversal code like I think 36% faster. So that was pretty cool, but it's still not as good as the it's still not as good as the original tiled one in this very simple test case, which is not like, yeah, we should really do a more comprehensive test, right? But we'll get there. Crap. Oh, I didn't enable the BVH stuff, so there wasn't really a BVH. Whoops, that could have been bad. Okay. So, oh. So, yeah, the BVH ray tracer is about 0.58 ms, and then the tiled one is about 0.13 ms. So, you know, it's way faster. And if you remember why we initially went on this journey, hey there, Zach. I'll explain what Froxels are in a minute. The reason why we went on this journey was because we was thinking about lighting, right? And was using screen space tiles to bin our spheres in, right? So we have a screen, it's split into tiles, and tiles like this, and we bin the spheres in a nice little array per that was a terrible array. So you got like an array of spheres in memory, and we'll just iterate over those spheres for all these pixels and see if we hit them. And that's how the tiled one works, right? But if we go back to this is me in the past me. This is an example of 128,000, roughly about, spheres being rendered on the screen at once. And this was about 4.7 ms, and it takes 1 ms to bin, right? That's a bit too much, too slow. So part of the problem with this is every screen tile was holds an array, and it was up to like 256. The screen tiles are like 16 by 16 pixels. So it holds up to 256 spheres, and it's kind of pre-allocated. Yeah, I think we'll probably solve this problem today actually as well. But so the issue is they were not in some kind of order. So what would happen is you'd have to basically iterate over all of the spheres and do raycast up to the maximum number that you have in there, and it would even if you hit one, say if you hit the third one, you have to iterate over all of them to see if you hit one that was closer. And it wasn't, and that's the reason why it was taking so long, is because you had to traverse over so many spheres and ray trace against all of them. So what I was thinking about doing is I need an acceleration structure that can work good from the view's perspective as well as in the world, right? Because we might want to do some sort of like ray tracing from inside the world and calculate lighting basically, or shadows, or have different a different sort of camera in a sense in the world, which maybe calculates like a shadow map or something, right? So if I needed more of a general acceleration structure, that's why we went and did this BVH. But turns out it's not it's going to be slower, and we wanted something ideally to be faster. So I was thinking the BVH would be better. And it still could be. We don't know with this very simple test scene, but chances are it's probably not going to be better. Hey there, Ansel. Hey there, Nico. How's it going? Why did I test on this small scale? Because I haven't got anything large yet. But what I'm doing is building up 3 different things that we can test in a larger scene in a bit. But we basically haven't built anything like a concept of a model or a concept of instances. It's just a bunch of spheres. That's the problem. So essentially, there's also a problem with the tile binning. The tile binning takes about 1 ms, 1 frame, and then the other frame takes 0.4 ms. Like, it's very weird. And the reason that it's a very spiky, very noisy performance. And the reason why that is because it uses atomics. And it just literally atomic adds into these screen tiles. And when they overlap, it gets really bad. When 2 threads overlap at the same time, it gets really bad, and it happens a lot. But if they happen to like not overlap at the same time, it's much better. So what we want to do is try another approach. So I want to have 3 approaches, right? A screen space tile binning that we want to test. I want to have a BVH version so this is to accelerate. These are all basically ray tracing, but these are different acceleration structures, right? So screen space only works from the camera's perspective, or the main camera's perspective. It might benefit from some kind of occlusion buffer at some point. We've got this BVH acceleration structure, which is probably going to be used for lighting in the end, but we definitely want to test it from the main camera's perspective as well to see how it compares. And then we're going to have this other one, which is basically an extension to this tiled one, and that'll be the Froxel based acceleration structure. So all the word Froxel means is basically frustum space voxels. So essentially it's a frustum grid. So this is the near plane, obviously. You'll have like a far plane, and basically you just want to where's the line tool? Good. Basically you just want to divide the screen up into grids. That's just a very minimal grid, but it's actually going to be a far larger grid. So essentially you have your X, you have your Y, and you have your Zs, right? And you're just basically creating a grid in frustum space. So this could probably benefit from some kind of occlusion as well. So we was looking at Froxels to do lighting with, right? We thought it was a really great idea to do lighting with initially. But then what I discovered is it wasn't great for lighting, because if you have a light over here that tries to sort of that just about reaches inside here, and you have a sphere there, this sphere won't be stored inside the Froxel, so you just won't get any sort of you just get light there where you shouldn't have got light, basically. So we're basically doing this screen space one, but in 3D instead. So this should hopefully minimize the amount of atomic overlaps, hopefully, because there's just more cells. But also solves the problem of depth, basically. So we could sort these guys in these screen tiles. That's something we can do. But also what we can do from this, these sort of screen space voxel method, right? So we'll just we'll go over every sphere. We'll bin the spheres inside these Froxels. So you got a sphere here. It'll obviously go in this left one and this right one, right? If you have a sphere like this, yeah, it's the same. It's the same. So the reason why you have them, the reason why this acceleration structure can help with the depth problem is, imagine if you have something like that, and you shoot a ray out for that pixel. When you test against this sphere, you'll test against all the spheres inside. You start from this Froxel, then that one, then this one. But these ones have nothing in it, so you really just skip them. You'll test all the spheres in this Froxel. This one doesn't hit. This one hits, right? And then we've finished all the spheres in the Froxel. But we found a hit, so we don't have to test any of the Froxels that come after. We can just skip these. So this is the benefit of doing essentially a 3D gridded version of the screen space tiles. Yeah. So what I want to have is I want to write this final acceleration structure, make it work, and then we'll go and basically expand the test scene, and then we can basically optimize and test all three of these on a much larger scene, and just see which ones end up being the best, basically. Yeah. So has anyone got any questions around that sort of thing? Going good though, but tired. About 6 concerts coming up next week. The next 2 weeks. Insane. How are you gonna manage that? Sure, I'm gonna be falling off. Just be like, yeah. Crazy. I don't even manage this, Russell. Right. So I want to start off by fixing the yeah. Okay, so I've basically fixed the problem off stream, so I need to go over that. The game was crashing when the ship flew too close to the screen, right? But now it works. So what was the problem? So I need to go over what that problem was. The problem was in the tile binning shader for this screen space acceleration structure that we have. This version here. It was this shader here, the tile binning one. What was happening? It was this part right here. See this clamp? This clamp didn't exist. So what was happening is it was getting some screen bounds, and the screen bounds were basically negative, or they were outside of the... Yeah, I think they were negative, something like that. And it was... Or infinity, or whatever it was, right? But But now what we've done is basically clamped it between 0 and obviously the number of tiles that we have along that axis. And that's obviously fixed the problem. So these loops were going on for an infinite amount of time. Yeah. So something I want to sort out first before we do this Froxel thing is I want to fix the problem with the tile binning. The problem with the tile binning is we have a fixed number of spheres per tile. There it is. This needs to go away. Right, we literally want to delete this variable. Like, it's just not good. So how are we going to get rid of it? So essentially what I want to do is have a pre-pass. I want to have a pre-pass which basically sees how much is going to see how many spheres are actually going to get added. And then we'll go over it, and then we'll allocate. Yeah, we'll see how many tile spheres actually go in a single tile. Then we allocate the memory for that tile from one massive linear array. And then I think we'll just go over it again. So it's got the cost of going over it twice, but it's the only way I think I can solve the method. What are Froxels? They're frustum voxels. So essentially we'll be doing a 3D version of a screen space tile binning. We'll be making it frustum based voxel binning, right? So it's a yeah. So this is a Froxel basically right here. Essentially it's just a grid in frustum space. So what sort of new arrays do I need? So I need an array to keep track of the maximum number that we can then use to allocate. And then we need probably a start index as well. So we need we just need a tile. All right, let's make another one of these guys. So the tile's gonna have like a start index where all the spheres go, and we'll have like a number. Right. Spheres count. So we'll just make a nice new buffer. So we'll go up to the initialize function, and we're just going to go ahead and find something we can just steal. So we've got the tiles buffer of tiles, sphere tile. Should really call it sphere tile, shouldn't I really? Because we're gonna have more stuff than just there's tile spheres and sphere tiles. Good names. So we like, where's the maximum number of these guys that we're gonna have? Yep, tile spheres tile cap. This will do it. Oh, it's already there. Well done. Tile sphere tile. Fantastic. Right, so we've got one of these boys now. So essentially, we need this to be cleared every frame. So what do we do with this sphere tile binning? Right, so we zero the sphere counts. Oh, we've got spheres counts already. Get rid of that one. Right, so taking this zero is going to be extra useful. And we're going to call it sphere tiles. So just zero that whole buffer. Boom. I could have just written a shader to do that, but you know, that also works. So we want one which is just going to sort of calculate sizes or whatever we call it. And then we do the other, and then we have an allocate shader, and then we have one which actually bins them. It is back. Oh yeah. Sphere tile or tile sphere? My brain. I know, right? It's what happens when you just write quick code to see if stuff goes fast. You just like, you know, just get messy. Just get messy. It'll get cleaned up later. So when we know what we want, we can just be like, right, all this code is going, this code stays, and we just you know, do a nice cleanup pass. It'd be good. So sphere tile binning, sphere tile sort of count. Or calculate counts. That's a good one. Count counts. So we go over all of the spheres. We're not going to write into any tile spheres. We're going to write to some sphere tile. Sphere tiles. And then, yes, this count goes away. Goodbye. The occlusion, yeah. See what's this method could still benefit from some kind of like occlusion buffer. We kind of like tried it out, a very cheap version out last time, and it didn't quite work. And we kind of just like changed gears and did the whole BVH thing. So when we're comparing the three methods, we definitely want to probably have some kind of occlusion buffer or something for the tile binning and these Froxel binning solutions. So see, this should be called tile grid dims. Much better name. Not sure if you need the output dims. You might do. Did we need those? Oh yes, yeah, we do. Of course we do. So that's to calculate the original bounding box. Right, and then we need another one, which is basically going to allocate. This needs to be read-write. So this allocates all the spheres. We just need the number of sphere tiles, I think, because you're just going over all of them and doing a... Wait, no, you need a sphere. But there needs to be like an integer somewhere where you sort of... We might need to make a buffer for it. Maybe we can have it as sphere. Essentially this is like sphere allocator. And you just increment integer. Maybe we can have this integer part of some bigger buffer with some other stuff in it, but for now that'd be fine. And then you do the actual binning. Yeah. Yes, the reason why we're making this change as well is like the Froxel system is going to work the same way. So it would just be easier if we just did this conversion and then copied it over and started in the Froxel-based binning. Because it's basically just extending this tile-based binning into the third dimension, effectively. So let's make 2 new shaders. Right. So tile counts. Calculate the counts. So you're going over every single sphere, and you're trying to, like, it is basically a copy of this one. And you're basically just counting, but you're not actually binning yet. This one is going to be called allocate or alloc. Yep. So this one just goes over all the tiles. So let's just write this one out because it's going to be dead easy. So you're just literally going to you're going to get a tile. So you'll be like BC sphere tiles. You obviously need some kind of if statement to say if I've gone past the number of tiles. So you go tile index. We can launch it 2D. Then you have to flatten it out anyway. Yeah, let's just do 1D, it's fine. So you get a number of tiles. So it goes out of bounds, then just end it. Tile index dot spheres start index equals, and then we basically get all of this, and we do our atomic add U32. I'm going to add to the address of BC spheres allocator, which we've got to make this array. Yeah, sphere allocator. We're going to add the number of spheres that we've counted in the previous shader, right? And that's how we're going to allocate. It's going to be dead simple to do. So essentially each thread is going to do this. But there's not going to be that many tiles, so hopefully it'll just be instant, right? So we need to modify this one quickly, and we need to say sphere tiles count. Excellent. So that's the most basic one out of the way. Kind of gonna have repeating code here, but it's fine. Just repeating code. So the way this shader works is, so we can ignore this code. This was to do with the occlusion buffer, but it basically calculates the. Wait a minute, I've had that video up still. This is the video where I implemented the occlusion part for it. There's the occlusion buffer, it was really bad. We could probably do a good second attempt at that at some point. I don't know what I'm really looking for in this video. Right, maybe not then. So essentially, we've just got like, let's make a new frustum, one that's not Froxelized. So essentially, we've got like a sphere in the world, right? We put we calculate a bounding box. We literally just do an axis line bounding box around it, and then we sort of like project. Yeah, it's that one and that one. We project these two, and it'll be these two if it was on the other side, and that goes in each 4 edges of the screen. We project those back to the near plane, and then we remap. Is that right? You project it back to the near plane to get how big it is on the screen. It's a very rough estimate. Yeah, and then we move it up into screen pixels, and then we essentially get those bounds. We round it to the nearest screen tile, and then we go over all the screen tiles and bin them. So this is fine for small spheres, really bad for big spheres. We probably want to extend it and have a bigger. We might want to have essentially different layers of screen tiles in the future to see if to extend this method a bit more. Maybe we can have essentially like a mip map, right? Where you'll if it's a very massive sphere, you'll have really massive tiles that you bin it in, and you just go over different tiles. Been wondering, do Froxel's grids get bigger as they get more distant from the camera? That's something you can do. Something we might do. It's something you probably should do. Like if you just did like a fix, you like, you know, for your these guys back here will probably be like very big anyway, right? So if you only store in a couple in here on like a usage rate, whereas these ones here are going to be like really, really small or whatever. So yeah, you're better off probably just making them bigger steps. That is correct. Using the diagram as a reference. Oh, I see. Yeah, it's not drawn to scale or anything. But yeah, they do get bigger. Yeah, the depth should go for. But yeah, these boxes will definitely be bigger. That's the point of. Yeah, point of it as well. Yeah, so this is calculating the counts. So all we have to do instead is we're not binning the spheres this time. We're simply inserting. So we're using that sort of tiles, sphere tiles. We're getting the tile index, and then we are doing a dot sphere counts, spheres count. I'm just going to add one to that. We're not getting an insert index, so hopefully, depending on the hardware, this could be quicker because it's not dependent on a return value, meaning that if you have, like theoretically, right, I'm not sure how all hardware works, but theoretically you should, if you have 2 different compute units that want to atomically add a value in memory somewhere, you don't have to the threads don't have to sort of wait. They technically don't have to get the value back from main memory, or not really main memory, maybe like a nearby cache, maybe level 2 cache or something. You don't have to sort of get the value back. You just have to sort of have it incremented. So maybe they could have some special bit of hardware, maybe, you know what I mean, to sort of like do the atomic incrementing potentially. I'm not sure. I just imagine that it could be possible. I'm not sure what hardware actually does though, to be fair. Like, so we just want an atomic add here, right? And so then all we need to do is, yeah, so just atomic add there, and we're done. So this one is then obviously just going to use that overall count here, and then just allocate a new start index, boom, and then the tile binning shader is going to go over it again. Calculate the bounds for a sphere again, right? And this time it's going to actually add it in, right? So where are we going to do this exactly? How are we going to calculate the new index? So see, if this becomes expensive, we could just store where it's index what the allocated index for it, basically. But if we can't, then we'll just yeah, if we can't, then we'll just like yeah. If it's more expensive, we'll just store the index into some array somewhere and just pick it up here and just avoid doing all of this and just go over and just read an index from the array and rather than recalculating it. But we'll see how that ends up when we optimize this some other time. Spheres counts. So what are we adding into now? Let's just do another field, right? Be easier. So we probably just want to add one called an insert index as well. That we can just, so that's obviously zeroed. Sphere tiles, spheres insert index. So you just add by one, there's your insert index. There's no check needed anymore. And then you just simply add it in. The start index though is spheres. And there we go. So that should be it from the oh, did I copy that 3 times? Or one more time than I needed to. Right, counts, alloc, binning. Right, good. So that should compile. We just got to hook it up CPU side. And then that should be the improvement for the tile binning. So it will not overflow the tiles anymore. And then we get started on the whole Froxel binning, which would be pretty cool. BC tile dims, where did that one go? I didn't go anywhere, I just didn't have it in there to begin with. Oh, I changed it to grid dims, didn't I? Right, what's this one missing? Oh, I need to index it like that. Don't I have sphere tiles? Right, tile binning needs sphere tiles. Right, which ones doesn't it need? Sphere counts can go. And this is read only. Excellent. Rightio. I need to call this grid. Right, so now we've just got to hook all these boys up. So, sphere tiles, that's our new buffer. These are the grid dims. Right, anything else that we added to this guy? So it was just these. Just 4 of them. It's good. Okay, so that one didn't really change. We just gotta... I think we'll make a buffer for an allocator as well. So that one on. Tile spheres. Right, spheres. Allocator. So, yeah, this just is a buffer with one element in it. Again, we should probably have some big buffer that just has a bunch of just miscellaneous stuff in it, right? But for now, just one U32 goes in there. And there we go. So, get back to here where we... What's going on? Okay. So this one needs to be the allocator. Sorry, calculates the counts. So this one needs spheres. Let's get these all in. So spheres, sphere tiles. It needs spheres counts, all spheres count, output dims, grid dims, size. Perfect. We just need to synchronize on these two, no occlusion. And now, see about the occlusion later. Right, that one's good. Good to go. Wait a minute. How are we launching this one? Yeah, we'll launch all this. Yeah, each thread gets a sphere. Just need to sort that one out there. Boom. So now this next one is sphere tile allocates. This just basically allocates the tiles their sphere memory. So this one is very basic. Just needs these 3 boys. So we need our sphere allocator. So let's get the sphere allocator in there. Boom. Then we need our sphere tiles. And then we just need the sphere tile counts. It's the number of sphere tiles that we got. So it's this. It's just the grid dimensions X, Y, right? Now we need read write on the allocator. Read write on the allocator. We need read write on the sphere tiles. Collision can go. This one needs to dispatch over all of the tiles, right? So it is tiles count divided by 32, but rounded up, right? Because we do 32 dispatch locally. I'll plop in that, and that'll just go there like that. So it's got one more to sort out, and that's the tile binning. So the tile binning, let's get all these in just in case. So this one we had before, but we've changed it. I know I did fix up these, but I think I just want to double check it, right? So we've got 4 of those guys, spheres count. Yep. Read only, write only, read only, read only. Right, it's read only. There we go. Okay. So that should be the new and upgraded tile binning process. Let's just quickly double check it before we launch it inside the shader code. Oh, what is this one doing? Oh, when we ray trace against it, we need to know what tile we're in and get that tile and go over those spheres. Got it. So this one needs the number of, it needs the sphere tiles rather than the counts. Well, hey. So we need to go, that's another read only. Where is it? I should really move this around the other way. We should build the tile ones together, you know? These are grid dims, which means this should be called grid dims as well. Grid dims. So this needs to be these sphere tiles, don't it? Okay. I don't know why that's divide by 8, because doesn't that shader use a tile binning? Cell size is a bit dangerous. Cool. Yeah, so that should be updated. I just want to check the shaders one more time. Right, so this is when we do the ray tracing. Base sphere index. So you want to just basically fetch that from the tile, sphere tiles. Sphere tiles dot spheres count, and then the other one is start index noise. So this should be no more. This guy should be no more. So we should get rid of it and fix all the compilers. Should only be 1 or 2. Tile spheres buffer. The overall number of spheres capacity. The thing is about the allocator though, is the allocator Yeah, the allocator should be where spheres cap. We should fix that. Right, apparently it's liking what's going on. Wait, why is that still here? Oh, it's commented out code. Yeah, so when we allocate, is it when we allocate? Yeah, we should min this. You're just gonna get a bunch of fighting at the end though, right? So we want to work out like the... I think it's fine to have the fighting problem. Maybe. So when you allocate, you want to find some kind of like spheres capacity overall. And that is... Well, not spheres cap, it's kind of like the max spheres start index that you could possibly have. So that would be essentially just like that, take that. And you can min it with the max. And that'll hopefully fix the problem if it overflows. Right, let's just quickly double check all of the spheres cap isn't... Oh boy. Put in the shared header. Right, we kind of got like 161,000 spheres as a capacity for now. Hoping to be able to push more, but we'll see where we get to. So, if we have this... Alright, so let's double check it. So we calculate the bounds. We're just going over the spheres, right? Same old stuff. This is the occlusion stuff that we kind of tried out and didn't really work out how we wanted, so we've paused it for now, basically. This, we just calculate a screen bounding box, a rough one, go over all the tiles, and then we count the number of spheres. Nice. Then we run the allocation pass afterwards. So let's just double check that quick. Oh, I didn't ever change the shaders. Binning. They're all the binning shaders, that's not good. Calculate the counts. Allocate. Oh, come on, there's not a... Ooh. Oh. Oops. Right, that would have just ran the wrong shader. That wouldn't have been good at all. Okay. So we calculate the counts. That looks fine to me. Allocate. We got to set the number of tiles. Get the tiles count. Max start index. Atomic add and then minute. Cool. Stop us from over allocating. Then the tile binning is basically the same shader as the count. But instead we add to the insert index. Get the start index which we allocated. And start index plus the insert index. And then put your sphere in there. Boom. So that should be it. Nothing else has changed, so it should just work out fine. Let's go. Right, if the stream dies, I'll be right back because this AMD hardware it likes to die if it doesn't work. Alright, we're still here. So that has added these guys, right? So calculating the counts is obviously about the same speed as the binning. So this is kind of the problem with the solution we've just done, right? Is we're essentially doubling the time it costs to actually bin these guys. But hopefully we can minimize that when we optimize this later, right? Yeah, so we calculate the counts, we allocate the tiles, and then we bin, then we render the spheres. Now, we are doing 2 ray tracers. This BVH1 is going to be on top, so it would fix any problems. So let's just quickly disable this sort of BVH ray traced version and see how that runs. Aha, not running well at all, is it? So, why is it not running well at all? Oh, we're not resetting the allocator. So the first frame is probably great. There we go. Boom. Cool. Yes, there's our spheres there. Rightio. So, yeah, let's get started on this Froxel thing next. I think that'd be good. Right, I'm just gonna quickly go and get a drink. And then we'll basically copy and paste over the tile binning. And we're gonna turn it into this Froxel based acceleration structure. And we'll go from there. Right, be right back. Right, welcome back everyone. So, let's get going with this sort of Froxel binning. So, we'll probably do a very similar thing where we calculate essentially counts. Yeah, we're going to do the same sort of thing. So, effectively, how do you so these aren't, they're not regular voxels, are they? They're not like, so how do you essentially bin spheres in this sort of grid, right? Well, so I was thinking about this today, and we just need to bin them in the grid, right? So if we can basically get a screen space bounding box, which we've already done with the tile binning, all we have to do is get the far left, so you get the screen space bounds, right? Where's the bugger? Oh, good. Right. So you get the screen space bounds. Then from there, you work out the screen tile, right? Yeah, from there you can work out the sort of X and Y screen tile. And now all you have to do is work out the depths, right? The depth part of it. So you can work out the X and Y by just bringing it back into, well, maybe you can bring it back into the near plane. Maybe you can bring the information out into the world, and do it that way. Yeah, maybe you can bring the information out to the world. You just need the far left point and the far right point. Let me draw a very exaggerated frustum for a second. All right, let's draw like some massive FOV, right? Field of view. So if you have a sphere like here, make it massive or whatever, I don't know, big. You go obviously going to the far left hand side, it goes through it, right? But so what am I trying to think of? So say if you have this point here, that's not going to do it, is it? Whereas if you did the axis on banner box corners. Hey, Intense Lurker, thank you so much. Yeah, man, doing good. Thank you. I just thought I'd put something different on. It was in the suggestions. Appreciate the sub, my friend. Welcome, welcome. But yeah, doing good. Thank you. Just trying to find ways to make my sphere rendering go fast. So we're trying out another acceleration structure. Another a view space acceleration structure this time instead of a screen space one. And then we're gonna start adding more content and just seeing how well these three different acceleration structures work with more content, right? But yeah, not doing bad. Nearly, I got like 1 week and 1 day left until I am off for Christmas, basically. That's gonna be pretty good. But yeah, hope you're doing good. So if we did it just on the far left, it's not going to be good for exaggerated things. We still need to do pick the appropriate corners. But if we pick we pick the corners of the bounding box that we can calculate. And then from that, we can leave it in world space. And we'll just move. Yeah, wait, but what am I trying to figure out? I'm trying to figure out the nearest X and Y, like, uh, X and Y tile, right? So if you bring it back into frustum space, you'll know right away how to round it. But in terms of, they've got even spacing. You can get the spacing at that depth. That's what you do. You get the tile width, you send it out at that depth, and then you could probably round it to the nearest. Will that work? No, that's cool, man. No worries. Yeah, here's the link. So I think what we might be able to do is, given a depth along a ray, it's just a depth. The depth is the same. Yeah, given a depth. Yeah, what is the size of this? What is the size of that? Basically, something like that. Wait, it's kind of hard. We basically need to work out the world space, or view. Do we want view space? Yeah, really, the sphere should be in. See, I haven't really got the whole sort of camera system sorted out yet either, which is a kind of an issue. We need to remember this stuff when we do it. But yeah, we need to be in view space. So relative from the view, looking at the sphere. And we can obviously know we'll know this is 0x 0y, right? In the middle of the middle, right? We can then work out sort of how big one of these cells are, basically, at this depth, but also what's the far left and far right. And from all this information, you can basically work out which Froxels you need to iterate over without a divide, which takes you back into this. You could divide and go back into screen space basically and do all calculations, but that requires division. We can just do some multipliers and bring stuff out and work with that. I think that'll be good. Okay, so let's just start writing the code, and I think we can do a good job of that. So we've got the tar binning. Let's copy these three, and we'll add a new one. So we're just gonna, so you still have your spheres allocator. We might run these at different times. Yeah, it's fun. Right, so replace tar with Froxel. Sphere Froxels. Right. Froxel, Froxel, Froxel. Right. So in the shed, we need to define a Froxel. What is, I think it's just going to be like a tile. We don't really necessarily need to know. Like, you know, we could treat these as planes basically, right? As a bunch of planes. And do some collision detection, but then I think it'd just be far too expensive. I think we can do that would be a more precise binning, but I think we do more of a crude version of a bounding box, I think. So something like Froxel. Yeah, we'll just probably do the same sort of thing. We have a sphere start index, insert index, that for now. And we'll go from there really, I think. So we need a sphere Froxels buffer. Cool. So how many Froxels we're gonna have? So we kind of need to know, like, we kind of need to have like a far plane, and I think we might. Yeah, we might have a far plane of maybe. So the far distance might be like 128 or something. I don't know. But and I kept it at power of 2. So your near is going to be at 1, and your far might be at 128. Yeah. So the first set of Froxels will be these. Next set will be twice as much, twice as much, twice as much, twice as much. So you'd have basically seven of them, right? So we'll probably do them like in log 2. If we do them in log 2, then they will sort of exponentially increase, right, in powers of 2, right? Does the far plane basically cap the frustum grid? Yes. So cap the frustum grid at so here. We kind of should have a far plane regardless, but you definitely need one when you do this sort of view space thing. So our far plane will be 128 right here. And this will allow for 7. I don't know if I've done 7. 1, 2, 3, 4, 5, 6, 7. Okay. Well, no, maybe I did 8. Okay. Anyway. Where this is definitely not to scale. This looks very even in a way, the Z. But the Z is going to exponentially increase log 2 scale. So, which would be pretty good. So we should say must be power of 2. It might not have to be a power of 2, but if it is, you get better efficiency with the maybe get better efficiency. You can just do log 2 of that number. It shouldn't be too hard. So many Froxels we're gonna have. So let's just say a max display where you've got this min size. Yeah, what do we do for a size of a tile in the end? We need to play around with that. Oh. Oh yeah. Yes, the idea is if you obviously have like a 4K screen, your tiles might want to be bigger. Yeah, so I had this sort of min tile size. Do the same sort of thing, I think. So I think it'll be based off the tile system. This Froxel one should be fine. So the number of Froxels will be the tile capacity times by just how many depths you're going to have, right? So we also need to have the number of like Froxel yeah, the number of Froxel Z cells along the Z, right? So that's be log 2 of 128, which will get you 7, right? Dun, 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 dun. So so you probably want to round that down, like floor it. So if someone does something that's not a power of 2, best of power 2 for Froxel binning. Then we cast that into U32 and kabam. So then you just times it by the number of Z cells and boom. So that's the Froxel capacity. And you just want to then all right. So that's your Froxel buffer. We also need to have our Froxel spheres buffer. One of these boys. And this basically just stores all of the spheres for a Froxel. They're inside of a Froxel, right? So, and this is just the maximum, an array of maximum number of spheres. We need another allocator. Right, so spheres allocator for the tiles. Tile spheres allocator. That's what we'll call it. I'm going to do another one. Why is that done twice? Oh yeah, that's fine, that's fine. They have a Froxel spheres allocator. Allocates all the Froxel spheres. Tile spheres allocator. Froxel spheres allocator. Boom. So we'll just allocate the allocator. Obviously, in future, we'll probably have, we'll definitely have one of these, right? But, you know. Did I spell Froxel wrong? Right, and that's a Froxel. No. These are in different orders. Grr. Something of that. Okay. So there are all of our buffers allocated now that we need to work with for now. So let's go and hook up the CPU side, and then we'll just go into the shader side and get this ball rolling. So let's hit F5 and find the errors. Boom, they're here. So, right, first of all, we don't have these guys defined, so let's go and define those quick. So in our shader code at the top, which has got some structures, these are our push constants that we upload to the GPU. So we're just going to go ahead and find our tile binning. Oh, this is our UI one. We did a lot of tile binning stuff on this. Here we go. So we'll take these guys and replace tile with Froxel. Alright. We might need to add a third dimension to this or something, but we'll see what happens when we get in the shader, right? Okay, so now we're back here, and less errors. So Froxel grid dims. We need to obviously calculate those, so let's go ahead and get there. So this is where we allocate the sphere grid dims. We're going to duplicate it, and now the Froxel. See, the Froxel size doesn't really make much sense anymore. Yeah, so you call it like Froxel dims, right? And we'll say something like times 3. No, but the Z is different each time, isn't it? Yeah, the Z will be in log. Maybe we can just always know that the Z is in log 2 space. And then just multiply it by the power of 2 when we want to use it. Yeah, which is dead easy, right? It's just a shift. It's a shift away, isn't it? So yeah, we'll call this the sort of XY dims. No, we'll call it XY size. Yeah, that'd be fine. So grid dims. So we need the grid dims to probably do dispatches across all the grids, but also to clamp stuff, right? So this one is going to be, just place a tile. Oh. All right. So we're doing this sort of XY size thing here. Right. Now this needs a third dimension. So to achieve that, I think we'll just be using that log 2 of where's that floor log 2 thing we did of far distance, right? Cast it into an integer. Boom. Right, so there's the necessary variables. So let's keep going. This now we just need XY size, so we'll probably change that in here. just the X and Y size, you see. These need to be a 3D thing now. Okay, so that's the first set of errors. This will fix up when we actually write the shaders. Froxel allocate, that should be the number of Froxels. We need to go over. Needs to have a Z component. Shoot. That's fine. And then this one is same as this guy, right? We need to change this to a Froxel XY size and 3D there. Okay, so that's everything CPU side. Now let's get inside the shader code and start going. So remember, these two are going to basically be the same for now. They're these binning and calculate the number of things that go inside of a Froxel. So literally by doing this, shader is going to do this one. And then the allocate one is just dead simple. We saw that in the tile one that we did today. So we're going to go ahead and just copy. So we're binning spheres into Froxels. Okay, so we're going to replace tile with Froxel. We should do uppercase first, because my lowercase does upper and lowercase at the same time. I'm doing my searches. Tile, and then Froxel. Oh yeah. Right. Okay, so now we can start with the actual programming. So, how do we bin a sphere into a Froxel, right? So we have a sphere in world space. We need to change it into view space, right? So I don't have, like, currently my world space is my view space. I don't have a moving camera at the moment. We need to add that in, but I'll put a comment in there. So when we add a moving camera, we'll obviously get that sorted out. So, we go over all the spheres. Each thread gets a sphere. We need to put that comment in the tile binner as well. Make sure you convert to do convert sphere from world space to view space. This needs to be in all of these guys. It needs to be in the tile binner as well, fair play. Right, Froxel. Okay, so we've got some like fixed camera stuff. Got some wide field of view because we can. And we get a sphere. This is some occlusion based. It uses like a bunch of MIP levels, that's why I said MIP. But yeah, it's like an occlusion thing, which we probably could just delete, to be fair. We can add occlusion, do a second try occlusion later. So all fits onto a screen this way. So we really, important takeaway is we have a pixel size at the near clip plane. This would be like 0.00 whatever. But it's yeah, it's great because we're going to be using this to work out how big the width, the X and Y is at a certain depth, and this can hopefully be used for this can hopefully be used to avoid some divisions, right, and to calculate which Froxels the sphere needs to be binned into. So sphere. So we need to calculate the center position in view space. So F32 times 3, center pos view space. So we'll simply just copy out the center position and we'll say 2D. Convert to view space. And same with the radius. Because technically you can scale. So yeah. There's that. Cool. So this used to get the screen bounds. That's not really a good idea. But we are going to borrow something from it. This calculates the bounding box. Actually, it was already relative from the camera to sphere APS. Right, I did an absolute. What's that about? Yeah, this is me going back into screen space. Why did you get the absolute one? Did I use that in the end? How did this one work again? I'm not sure. Did I reapply the sign anywhere? How did that work then? Oh well. I don't think I need to worry about that one. So yeah, I think we just need the bounding box. Yeah, exactly. No comments. Past me, ruined me, current me. Damn that person. But it's fine. I was just sidetracked and anyway looking at stuff I shouldn't have been. It's cool. So I think I want to get a bounding box around the sphere, right? So bounding box around the sphere. And then we want to use the front of it. The front left of it. Yeah, so this will go to the bottom left front, right? So you want to say like, yeah, min max. Radius view space, radius view space. Okay, so with this, right. So now how do we know So we can basically get this line, you know, we've got a box around it. You know, axis unbounded box around this to go. So we can say, we've got to figure out basically where is the furthest left. So if we get the front, yeah, the bottom left is not the one that we want if it's on the right hand side. Sorry, the bottom left is not the one that we want to use if it's on the top left hand side of the screen, because the distortion, you get distortion, right? You can have a, damn, all these view frustums in my way. So you can have a, you have a view like something like this, right? That's terrible. So you have a view something like this, right? I don't know why I drew this cross, but anyway. This is the origin of the camera. Your sphere up here is going to be distorted more towards the top right. Your sphere is going to be distorted more towards the top left like that, and the bottom left like that. Sorry, bottom right and the bottom left like this. So when you draw your bounding box around it, right, technically, it might look like this on the screen. On the screen, it will kind of look like this. Is that okay? It's not okay, is it? Because technically, these are screen space tiles going outward, right? Yeah, the screen space tiles going outward. So the furthest left is actually on the top left in this case, and the furthest left in this case would be the bottom left, right? Furthest left would be the top left, be the bottom left. So yeah, it just depends on the y-axis there. So the way we solved it in the other thing is we basically just like absoluted the value, right? We just absoluted it and just only dealt with this problem. We might have to do a very similar thing. I don't get how how did I move it back? So when I dealt with the absolute version of it, I got it in absolute, and then I got this near clip space, right? Lovely naming. Then we calculate the size, right? Because when you brought back the half dimensions, then we brought back the original position, right? I think that was okay. That works. So I only did it to calculate the sizing. Right. We could also just work out based on the sign what it is and figure out if we need min or max, basically. And do some multipliers. You can kind of make it branchless, I reckon. Yeah, we just need the sort of preferred. So you need a preferred left, and you need the preferred right. And then obviously preferred top, preferred bottom. Wait, does the distortion only it affects the top, bottom as well, doesn't it? Yeah. So you need a way to work out the preferred. Do we get it from the right? Okay. So I could use the sine function, which would give us -1 or 1, depending on if it's negative or positive. We can use that. Yeah. Actually, I don't know if we could use it because min and max could be across on the negative and then on the positive side. So maybe it's not a good idea to do it with sine. Right, so what problem do we actually need to solve? So we need to calculate the bounding box so that we can literally calculate the depth value at this depth. No, okay. We need the bounding box. We need the furthest left value so that we can tell what. Yeah, okay. So we need the depth so we can calculate how big each Froxel is at this depth, right? And then we can also tell how big the whole width is, right? And so we can basically figure out where to essentially start looking, because you can have a big one and you basically want to put it in all of these guys. So you don't want to know where to start looking. So then you need the furthest left value on the screen and the furthest right value on the screen. And bottom and top, obviously. Okay. So yeah, absolute and it won't do anything. We'll calculate an absolute space. Yeah, maybe calculate it in absolute space. Yeah, maybe we can do it this way, I think. ABS. Okay. Then we just need to know if we need to flip this back, basically. Or flip the yeah, so what do we care about? We care about the nearest yeah, I guess we just need something like this actually. We don't really need a bounding box per se. So we need like a left. And then we need a right. And a bottom top. Then you need your near. I don't think you need the far. So your near would be Z minus. Okay, so what do we need from this now? So the furthest left, you need left. Wait a minute, that's only if you transform it back into screen space. You have to worry about this problem. Yeah, so okay, so on the top right of the screen, so we might need the top and right initially. Would be the most distorted. The top and right would be most distorted if we absolute it, okay. Does this matter? That's in screen space though. It's distorted. Whereas we're in view space, it won't be distorted. Ah, I remember this drawing. This one. If you just did the left middle, you wouldn't get it. Yeah, but it's because we're coming out from screen space, and it would be distorted in the world. So what do you need to do? You need to get the furthest left. So at this depth, we can know the width of the Froxel, for instance, and we just have to check if it might just be fine. It might just be fine. We don't have to absolute any of it, I think. So we just need to know the left and right. And far. We might not need an absolute. Thinking about it. To absolute it and do some, because that was only when we moved into screen space. Right, let's just roll with this and see how it goes. What is a Froxel? It's basically a screen space, sorry, a frustum voxel. So rather than binning our spheres into screen space tiles, we're binning them into frustum grid. So this is a Froxel right here. Yeah, so I think we can just say at this depth, so we'll call it near depth. How big is a Froxel? So if we've got ourselves a Froxel in Froxel XY size, that's in screen space. So we want to move this from screen space to near clip space. So That's the size of a pixel at a near clip plane. We're putting the aspect ratio as well, to be honest. So on aspect ratio, we need to work out the size of a Froxel DIMS in near clip space. So that would be so this is the size of a pixel at the near clip plane. So that would be, yeah, so you would do something like Froxel XY size times by this times by AR, and then it's BC Froxel multiplied by that. So yeah, to get the aspect ratio correct, or to get it to account for the aspect ratio, we also need to multiply by the aspect ratio for the width. So that is it in near clip space. So this guy right here. So this is at 1, distance at 1 from the camera, from the camera origin. So what's at 1 when it's 90 degrees, I think, but yeah. No, 90, so it's a little bit different. Now we need to go into view space. So where is it, view space? So for that, we need to multiply the near clip space with the near depth. So it's just mol S and voila. So that brings your Froxel dimensions out into view space. So we'll know how big a single Froxel is now at that specific point right there. So now we just need to know how big are all of the Froxels at that depth. So Froxel, or maybe we want to call it view frustum width at depth, or we should call it DIMS at depth. Probably a bit better name, right? So how big is a frustum? How big is the frustum width, right? So that's the near clip height. So the near clip width is the height times the aspect ratio, right? So that will get you the near clip width. And from that, we can get the frustum width at depth by simply just multiplying. So that's obviously just a scalar. But yeah, by multiplying this by the near depth, right? So now with that information, we have yeah, maybe we need it actually in a vector. Frustum DIMS at width. So that'll just be, and there'd be a height version as well, and voila. Okay, so now we've got the x and y. I was thinking about it just I only needed the width because we obviously did it from a top-down view here. But yeah, I need the height as well, obviously. So now we've got the X and Y. Yeah, so we need to round. So obviously this is 0 on the x-axis. This is 0, right? It's in the middle. So this is negative going that way, and that's positive going this way. So what we could do is, yeah, we've basically just got to round our sphere, not our position, right? The left-hand side, round our left down to the nearest of Froxel dims at depth, right? Because if that is 0, if this is 0, this whole line here, then obviously to get to here, it's just rounded down, right? So I've got a lovely function for that. So we basically just want to round down to a multiple. So we want to get our sort of Froxel min, and our Froxel min is round down, round to, get this, round down to multiple. F32 times 2, is that a thing? It might not be a thing. Seems like a thing. Round down to multiple F32. Yeah, so we want to round down this guy. Wait. No, round down left and bottom. You know, maybe they were better off being vectors, to be honest. It doesn't really matter, I think. Scalars are fine. Doesn't really make any performance difference in shaders. Everything is kind of scalarized. Min, max. That's only your XY though. Round up to multiple. Fantastic. Right, so those were compiling. So this will get us the min and max along the yeah, this will get us like essentially in this doesn't really get us Froxel min, to be honest. It gets it in view space. So we need to translate that out into yeah, so this is so you then need to like add half. You need to add half and then take away a half, basically, isn't it? Oh, sorry, divide by 2. Add half and divide by 2 to convert it from signed space to unsigned space. And that will get you a min and max XY. But you still need a min and max on the Z. But let's just do the X and Y for now. Yeah, because the Z's a bit different. It's log 2 space, isn't it? That it's doing. So min max. Yeah, so why don't we turn it into turn it into an integer first. Min-max signed, we'll call it. So that would be, if we just do a divide. We need to divide it by the Froxel dims at depth. So divided by the dims, and that will get us... Yeah, why am I doing all of this? Yeah, continue to floor that. Yeah, it might be a more elegant way to do that. Because you round it to a nearest multiple of it, and then you're just dividing it. Whereas if you just did the division by it, then rounded it, that would be it really. So I think you can just do this, right? You can swap it around. So this will be floor. This would then be, yeah, you could probably just get it all in one go. Let's rewrite it. So U32 Froxel min x. So we just did left divided by Froxel dims at depth dot x, right? And then we just floor that. Then the y is bottom. Then you just repeat that. Sorry, right, top, and then seal. Boom. Okay, so that's literally, yeah, then we just need to add half now, I think. Because you're in negative, this would be -1. Wait, what would it be? That's interesting. What would it be? Yeah, this would be 0. This would be 1. -2, -1. So you'll need to just add BC Froxel grid dims.x divided by 2, right? Y and Y. Excellent. So we're nearly there to the point where we can actually just bin them in the tiles, in the Froxels rather. We just need the Z now, right? So the Z, see, so I was thinking before I start the stream that I might only need to bin it in a single Z. Let's just run through that quickly. The reason why I was thinking you only need it in a single Z is because the way the ray tracing is going to work is you'll ray trace against, you know, this one is closest to this one, say. So you just bin it in there. You won't bother binning it in here, right? So you just bin it in this one. So when you ray trace against it, you would simply just, maybe I should do a different example. Let's make it a bit bigger. Make it just a little bit go into there. Right. So it gets bent into this guy. So you ray trace, every pixel that goes through here is going to ray trace against this one, right? And the reason why, yeah. And if you hit it, yeah, I think it's fine. I think it's fine. So even if you do that, right, technically it's binned into here, so we'll still ray trace against it. And even as here, it's still binned into there, or ray trace against it. When we are looking at this box, and you find the closest hit, I think that's fine. Yeah, so the Z is special. There's two things that make it special. You don't have a min and max Z Froxel, you have a single Z Froxel. So this means we're binning into less. We're binning into less places, right? So we only grid across the, when you go do multiple X and Ys, like the screen space, we're going to do multiple X and Ys when we bin it. But we're going to do one, but we've got different Z layers that we could be binning it into, which is interesting. So to select the Z, firstly, we need to log to the depth, right? So there's your near depth. You want to bring it down into log 2 space, right? So our far plane is, so you want to be careful where we want to basically get rid of stuff that goes outside of the frustum, outside of the grid dims. Yeah, if it goes outside the grid dims, we've got to get rid of it. So we've got to be careful about that. So we log to that. So if it's 128, we get 7. If it's 64, we get 5. Sorry, we get 6. Sorry. If it's 32, we get 5. Right, it's just log 2. And then we floor it, right? Because we want the closest one. And then that is the Froxel that we're going into, right? And that is not going to be signed. So you don't have to worry about adding anything. Excellent. So now what we've got to do is we've got to be like, right, is our sphere inside the frust, like, we should really check if the sphere is inside a frustum a different way. Because you're kind of doing all of this calculation when you might be able to do a very simple sphere versus frustum calculation. I don't know if there is one I can find. Yeah. But we should really make, because we're about to use this in a for loop. And we don't really want to clamp it. Because if we clamp it, wait a minute, is that clamping a bad idea? Yeah, I think the clamping is a bad idea. If it goes outside of the bounds, we should just not bin it. That's something, and we're binning it regardless. Not good. Right, 2 seconds, I need to go and use the loop. Be right back. Right, welcome back everybody. So we actually need to fix that in the screen one. That's really bad. I did that off stream, I didn't realize it was a bad fix. We don't want to clamp it. We want to literally check if we're out of bounds. Like, if any of these are... Wait a minute. No, you don't want to clamp it. Yeah, you don't want to check if you're out of bounds. Yeah, if you clamp it, it'll be fine because it'll basically do 0 and it'll just not do a loop at all. That's fine. That's fine. Okay, so what do we need to do now when we bin these guys into these Froxels? So convert the bounds into... This is in Froxel space already. So we can get rid of all of this. Wait, I think we want to clamp it. So here we're clamping... I think this is right. So clamp between 0 and what? I think it's just the Froxel dims. We will want no divided round up. Froxel grid dims, that's it. Min and max between all of that. Min and max inclusive, so that'll be fine. Yep. Now for the Z. What are we doing with the clamp there? So for the Z, it'll just be 0 to... Yeah, I got dims along there as well, isn't it? Excellent. Cool. So now we have to just do a for loop, and it's just the same for loop as we did in the tile one. But we just do... We've got a bit different, right? We have vectors in the other one, but here we just do Froxel min x, or min y rather. Froxel min y, Froxel max y. Just gotta be careful. So if we say, well, yeah, that'll be 0, 0, 1, 2. So, yeah, that's fine, that's fine. That is all fine. Oh yeah. So this is going to go over all your Froxels. Now to calculate your Froxel thing. So the thing is about these guys, right, is I want... See, it would be better... Yeah. It'd be better if we do... If we go Z first. Because we kind of want to go over... We want that to be cache friendly, right? So the way we should really allocate these is it should be plus... Damn it. Then all of this times the number of z's. I think that's right. Plus z. Seems legit. So you're doing like all of those. So if you have like some xy's, you go, hey, all of those x and y's multiplied by the z, right? So say if this is x and y's, multiplied by all the z's, gets you all of these guys. Yeah. Plus the z. Yeah, that's right. Gotcha. So your Froxel index. But what? Yeah, I don't really care about the order they put in x and y. Okay, then sphere Froxels. Excellent. Perfect. So that should be how we calculate the counts. Now it's got to allocate our Froxels. See, this, I think we could do better. This is going to be random. It's literally going to be random. The way how it assigns its start index. What I really should have is all of the spheres that go through all of these layers should actually be next to each other in memory. Yeah, there's ways we can do that very easily. So instead we should go over all of the xy's. Then you go down all the z's, count all the z's up. Right, and since the Froxel z's are in, you can go over all of them, count them all up, do one atomic add, and then just go over them again and assign it, set it up. It should be manageable. That Froxel alloc, what did we do? Did we just do the xy's? That's that. Froxel's count. Right, do we want number tile? I think we want tiles. And we'll go down the Z depth. Yeah, I'm not sure. I don't think we're doing it. Yeah, we'll make this tiles. Right, I think this could be pretty good actually, the way we do this. So your Froxel's XY, that'll just be your tiles count. Dispatch for number of tiles. Okay, so what we'll do is we'll introduce a lovely for loop. Love me a good lovely for loop. So this will be our Froxel index, and it's going to be tile index, right, Froxel start. So that's tile index multiplied by the number of Froxel grid. Have I got a Froxel grid dims in here? If not, we need one. No, we just need the number of depths, isn't it? Number of depths. Which we can just get from here. Froxel Z size, I guess. This would be casted into an integer. Yeah, I'm not sure if compilers will optimize that out. And we floor it. Alright. So times by that number plus yeah, so then the end index, or the number of, you already got it, there's the number, okay? Oh, we still need an end index, I think. So it's just start index plus that rate. Okay, so so you have your Froxel start, and you have your, damn it, Froxel index less than Froxel end index. Froxel is such a weird word to spell on the keyboard. Alright. So here we're simply just going to go over all of the Froxels and just calculate how many spheres. Total spheres in tile, right? So that's just going to start with 0, and then we're just going to accumulate that in this for loop, like so. Then we're going to allocate. Tile spheres start index. So we just allocate from the total number of spheres in tile, right, inside a single screen tile. And then we simply just, now we do another for loop. Yeah, let's just get one of them. And then we simply just make it based on this one plus the number of spheres that you have. Where's the spheres count? Oh, you want to accumulate it, isn't it? Yeah, then you add this number to it. The number that your Froxel has. So the next Froxel gets the set after it, right? And then you min it with the max number of spheres that could possibly be allocated. So, well, you get some artifacts there, wouldn't you? It's fine. So this stops basically overflowing the buffer. Bit of a hack, but it'd be fine. Okay, that's pretty sweet. So let's just double check that. So we've got these screen tiles, and they have, you got these screen tiles, but they also have, they have some depth to them. You have they have layers basically into the view space. So you're simply getting the tile index, and you get how many z's there are. You get the start index. That's wrong. No, that's right. That's right. Start and end Froxel. So you just iterate over all of them in a array, going down 1z tile, and you're counting how many spheres are in each of those. Accumulate that, get the total number, allocate. Allocate yourself a start index. So now they're all going to be linear, which is going to be super great for performance when we ray trace, because all the spheres will be linear. And then you simply if all the spheres are going to be linear anyway, yeah, we still need to know how many are in there in a start index so we can early out, basically. That's pretty cool. So you got a number of Froxel. Yeah, then you have the Froxels again, and basically just get the get this max sphere start index just in case we overflow, and well, basically you can have overlapping memory at that point, but it's fine. So you get artifacts. So you accumulate into this guy based on number of Froxels and spheres in each Froxel, and then you can set the start index based on that number or that insert that you accumulate. Cool. So they're all allocated now. So the final thing is Froxel binning, like proper binning, and that is simply a copy paste of this guy, the one that calculates how many spheres fit in a Froxel, but this time we actually put them in there. And again, we could probably just store the final value in an array somewhere and just, make the shader dead simple. But this is not what we're doing today, is making it. We're not optimizing it today, are we? In the future, I want to see if that is an actual optimization. And then that'd be cool. It'll be like, oh, this actually helps, and then we go and do that. And then we, see a number go down, which is a nice feeling, right? Number go down. So Froxel binning, we do the same thing again. We just calculate the min and max, but instead of where's the tile binning code? The tile version. Right here. So for the Froxel binning, it's basically the same thing. You do it on the insert index. Instead, calculate your Froxel spheres. That's what we need. Froxel. Yeah, so we just basically copy a sphere into a linear array now. Okay. That's all we're doing. Jobs are good. Right, that should be that should literally be it. Where's the Z? Plus Froxel Z. Huh. Oh, it's on the counts one. Okay, of course. So the other one fails on that as well. Excellent. Rightio. So let's just quickly double check the CPU side and make sure all the inputs are coming through as we expect. And then we can simply run it and see if it crashes and burns the whole system. So this all compiles apparently. So for the calculate, we're just launching a number of, like, each thread gets a sphere and it just tries to, it counts how big a Froxel needs to be. This one goes over all of the Froxels and allocates. It just goes over all the tiles, and then it will go down all the Froxels for that tile, right? And allocate a range of where the spheres need to go. Then the binning actually goes and bins them in there. Make sure we got these right. Okay, this actually looks pretty good. So as you see, this crashes and burns my PC. Very much. Froxels finally, I know, right? I convinced myself that I shouldn't be doing Froxels, and then we went on the whole BVH thing. But after I've done the BVH thing, I'm like, maybe Froxels could work. But we're just binning the spheres in Froxel space. Because the basic gist is, the tile binning is better than in this current test scene, which is the most basic test scene ever, right? The BVH acceleration structure isn't actually as good as a simple screen space acceleration structure. So I'm doing an upgraded version now, which is the Froxel one. So initially I was thinking, you know what, let's have one acceleration structure to rule them all. For in-world rays that we need to shoot and do lighting with, we'll use the BVH. And I was like, from the screen we use the BVH as well, but it's not as fast. So I'm getting 3 solutions now. Right. We're doing the tiled one, and remember with the tiled one I had some problems where I fixed allocated the tiles to 256 spheres per tile. I fixed that problem now. So we basically do a 2-pass system where we try to bin them and just count it. Then we allocate them based on the counts, and then we actually bin them properly a second time. So it basically doubles the time it takes to bin, but I think maybe we can optimize that by not running the same code twice. But we've basically done the same thing with the Froxels as the tiles basically. So I'm hoping to have 3 acceleration structures to compare when we add tons and tons of content in. We'll make up a nice scene with stuff, and we'll just see how good we can make it look with a certain number of balls and how many balls that we can put on the screen basically, and just see how well it actually works. Awesome. Thank you for the compliment, appreciate it. So yeah, the stream could die, but I'll be right back if it does. So hopefully it doesn't crash and burn. Fingers crossed. Here we go. All right, ran. Excellent. Yeah, I know, right? It happens all the time. It's so annoying. Like AMD hardware. So it's actually, so the Froxel allocate is actually just as slow as it is to count all those. Right, so it's because it's the damn for loops, but I want it to be linear, but it's fine. So it turns out it's slightly quicker doing Froxel binning. Slightly quicker. I was expecting it to be, if it wasn't for the allocation being more complicated, it could actually be a lot more quicker. But yeah, I think we can basically reduce, anyway. I think I said earlier about the binning. It's just duplicated code for these two. We could probably just snub this one down to like 0.0001 ms or whatever, right? That's fine. Jumpy pixels? There's jumpy pixels. Oh yeah, fix the problem now so we go close to the screen. Ooh. Where's the jumpy pixels? On the right. Ah, these guys. That could, got it. Yeah, no, that's probably my anti-aliasing. Basically what I've got, so it's not anti-aliased because of the way it's been colored. There's something going on. No, I've not TAA. We're not doing TAA. Yeah, I'm not a fan of temporal. Basically, we're doing anti-aliasing when we ray trace the spheres, and you might be like, "Well, it's not anti-aliased." Yeah, because I think I broke it or something. But that's basically what's happening. Is we're getting like pixel dust around the edges, and it's a bit broken. Yeah, we're getting anti-aliasing dust around the edges. So now to render these Froxels, it's basically just a copy paste of a shader. Geodust anti-aliasing, yep. That's all we need. Now I'm probably excited. It's making the shader run twice as slow. But if it means we can get anti-aliasing, or some 50% to 100% slower. But if it means we can get like proper anti-aliasing and not this post-FX stuff that people do, you know, deferred anti-aliasing, it would be great. You know, do it while you draw it, because it'll just look nicer. So we take the tiled ray tracer. Here it is, and we'll call it Froxel. I think we'll just be able to jam this guy out within minutes, basically. Should be pretty cool. And then in the next streams we can literally like put models in. No, we do cameras, like an actual moving camera, fix all that up. Tons of good stuff. So let's. Right. There's tons of crap to remove from this. I can tell you that now. Froxel. Cell size, we're doing the same thing, cell size? Yeah. Right. So we need our Froxel spheres. We need our Froxels that we're looking over. So I think we need an extra loop. Did I miss the benchmark? You did for the... Yes, slightly. You missed the benchmark when we did all the binning stuff. Turns out it's slightly quicker. Oh, no. It's not a ray tracer yet. We're just benchmarking the binning. The Froxel binning is, in this very simple case, is a bit quicker than the tile binning. But yeah. Basically, it's a little bit quicker. We're doing the ray tracing now. I expect the ray tracing to actually be a bit slower. But it's going to be it's going to be slower because of the way the Froxels fit into. You only have one model, basically. When you have multiple models, it will definitely going to be quicker. Like you just basically be able to skip the background spheres. We can early out, so it'd be good. Froxel dims. See, I don't know how much of this stuff I need. But let's just get in there. Let's go ham. Right, Froxel XY size. So I guess your tile coordinate. Tile index. So we need like a Froxel start index, shall we? Froxel start index. Z size, that'll be Froxel grid dims.z. Number of spheres, well these are now Froxel spheres. Wait, no, sphere Froxels. Damn it, I misspelled it. Right. We need this for later. Let's put some dummy in there for a minute. We'll come back and get these when we do a loop. Here's our pixel coordinate. Get our ray direction. Wait, let me just double check the CPU side. I just want to sort it all out. Oh no, we'll do it later. So, bunch of stuff. We're gonna get rid of this because I think I tried to sort it at some point. There's some occlusion texture stuff. I just want to get rid of all these. All this sort of stuff that doesn't need to exist. This is to debug the bounds. Right, here we go. So get into the actual loop. So this loop here, we need a couple of loops. We need Froxel index. Something like this. We need to tab all of this in. Then we go over all the spheres. Now those two things that are left earlier, I'm going to get these guys. And we'll say, right, Froxel index, you get the base sphere index, and you get a number of spheres. You go over all the Froxel spheres. Yeah. These are going to be linear in memory. All of them, even through all the Froxels, they've been copied into be linear in memory. That's pretty nice. Then we do the standard ray tracing stuff. I'm yet to optimize this and make this better because I'm not, like, we've not done any lighting or anything, so I'm not really fussed about this being the best because the lighting is going to take up some performance as well. So, you know, it's kind of, yeah, it's kind of one of them. It's not going to be misleading, basically. This value, I don't think. Yeah, maybe we should share some of this code between the 3 different versions that we actually have because we just copied and pasted it right now. But yeah, so now we're getting the Froxels. Now the thing is we can actually early out. How do we early out? Well, we found a hit. Like, we do found a hit, right? Yeah, so we found a hit. Inside, so these Froxels and these spheres inside of a Froxel are not sorted, but they're sorted by depth if they're in a different Froxel, right? But inside a Froxel, they're not sorted. So if you've found a hit and not found a hit, right? But if you found a hit, you can end. And this is where part of the optimization is going to come in from this. Because if you have maybe 1,000 spheres in a tile, right? That's a lot of spheres. But they're broken up into different gridded areas. Bear in mind, these are, you know, say if you've hit a sphere here, you don't need to check the rest of these buggers. So that's pretty cool. And also bear in mind this, like, this looks even, this depth, but it's not even. We use a power of 2. Like, we still number this one 0, 1, 2, 3, and so on. But it's actually the depth is in log 2 space, basically. Yeah. Okay, so that should literally be it. It's not that much of a difference. So let's see if we crash and burn the PC. Just got to fix the CPU side. Froxel. Hey, the GP side is complaining. Wait, we didn't times by a Froxel size Y, is that fine? No, it's fine, that's fine. Wait a minute, I think I buggered something up. Let me just double check it. We'll get it compiling and I'll double check some logic. Because things could crash and burn. Oh yeah, Foxel. Foxel's the new... yeah. It's just so much easier to type and my fingers just always do it for some reason. Right. Um... Seriously? Oh, I did it again. Damn it. Right, let's go sort this guy here. Everywhere. Right, so the bit of logic that I think I actually got wrong is when we multiplied alloc. Right, and I did it in this other place as well, I've got to fix it. So, Froxel alloc. Wait, where do we times by the number of z's? Oh, it's not. It's here, isn't it? Sorry, it's in the calculate number of spheres in a Froxel shader. So to get the number of like I want to work out basically every other single Froxel, right, except for my one, and you know, to have a start index basically. Civetted. Yeah, it might just be easier just to picture in my head really, because drawing it's gonna be hard. It's 3D. It's a 3D grid basically. So in a 3D grid, imagine all of them are selected except for the final one at the top right or something like that. And I want to get the start index here. So that's going to be, so y times x. Hey Levy Dragon, how's it going? Yeah, Frog Pixel, yeah, one of those. No, Froxel is a voxel in frustum space. So basically, If you remember the screen space tiling that we did, right? Well, we were sorry, yeah, the screen space tile binning that we did. Imagine just that tile binning just has layers, right? And that's all it is. So there's your original layer. Like this is your original layer here, and then you just have in extra layers, right? That's all it is. And we're just spinning the spheres in there. So we're adding another method. So we can test out 3 methods when we add more content and just see what the performance would be like with the different methods of accelerating our ray tracing. Yeah, we rebuild it every frame, a bit like the tiles. But yeah, whereas the acceleration structure, you don't have to rebuild it every time. That's the benefit of that one. But I'm thinking we'll probably need to have, like, after seeing the performance of the BVH stuff, at this current point, which is not for certain, it seems like a screen space solution will be great for the primary rays that you used to render with. But for everything to do with lighting, the BVH is gonna be the thing basically. So we're gonna come up with 3 solutions, optimize the living crap out of them. Sorry. Yeah, we'll get 3 solutions in. We'll build a lovely test scene with different models and instances of those models, and then we'll just optimize everything, and then just pick the best one for that. So yeah, that's gonna be the plan. It's gonna be good. And then after that, we can actually do some lighting. Yeah, it's gonna be awesome. Yeah, after that, we can probably clean up some code and actually do some lighting. Yeah, that stuff. Yeah, imagine you've got like a 3D grid, except for the top right one hasn't, when you get the start index, and all of these are linear, right? Left, right. And then we wanna. So I've just got pictures in my head because it's just impossible to draw past this point. So y times x will get you up to yeah. So if you're yeah, so you say you have it on the final y, right? Then you say plus x. Okay, so that will get you in 2D. It will get you all of them on except for the top right cell, right? And then you multiply that by the depth. Yeah, that's right. Okay, that's good. I just wanted to make sure I got that right. And then that will basically have all of them on except for that final top right depth one. Fair play, man. Do you just like? Are you quite tired after work? Or do you just get, or do you get kind of like burnt out? Right. If the stream dies, I'll be right back. But it shouldn't die, right? Right? Believe in me. Right. Thank you for believing. It didn't die. Not tired, just not motivated. Fair play. Hmm. Like, are you like? Do you not have? Oh wow, those are not rendering right. Do you not have like something you really want to do, or is it just like the project feels too big that you just feel like you never finish it or something? Yeah, try something new. Get your feet wet. Hey, Funk, how you doing? Right, so we disable the tile renderer, the tile binning renderer. This is great. So as you get closer to the edge, it buggers up. Okay, so our binning is a bit buggered. It ain't bad for a first attempt. So, right, let's analyze our Froxel thing quickly. We were so close. Um, right, so wait, what could it possibly be? So these look fine to me, right? The left, rights, they're all looking good. Froxel dims at depth. Alright, let's go from here. This is fine. This was new. Aspect ratio, that's fine. Because you're going towards the width from the height, right? Width from the height. Yeah, see the near clip plane width. Pixel size and near clip plane. Interesting. Do we use this? Oh yeah, but we times it by AR. That's fine. We times it via the assault rifle. Completely fine. So you've you get your sphere. We get this view space sphere. This was fine. Then we move our Froxel dims from the near clip plane out. We move it from the near clip plane, which is here, size of that Froxel, out to here, right? Ignore that trading bit there, that's wrong. Then we get the frustum dimensions at depth, the near clip plane width and height. Times by the depth. See, the width seems to be a bit wrong. Maybe we need aspect ratio here. Should we put aspect ratio down and see what happens? I don't know if we need it though. Give it a go. Wait, I didn't even use this variable? I didn't even use this variable. What am I doing? That could be why then. Oh no, maybe I didn't need the frustum dims. I always need to know if it's a multiple. Yeah, we don't need these. Okay. So if you divide by the... So you at your left. You divide by the... That's the dimensions. At that depth. So that'll get you like -1, basically, for this box. because this is 0 in the middle. Like X and Y is 0 in view space. So you're getting the view space. Yes, in view space. Then you add grid dims divided by 2. Yes, what happens if it's an odd number? Did you matrix in it? Well, yeah, this is kind of a 2D matrix, but technically you did it in 3D. But yeah, it's like a 3D grid, yeah. Of view space voxels, right? Frusted voxels. So if that's an odd number, that's a problemo. But they're not, it's 16, right? It's going to be 16, but that's fine. Yeah, so that's not the problem. Right, nothing's standing out. So we run it again just to get a bit of a feel. Like the y-axis, oh, is not good either. Whoopsie. Oh, my days. Oh, I think I know what's going on. Yeah, I think it's that problem I was talking about where it gets distorted near the corners, right? Yeah, we need to solve for that. Going along with the music, that's good. Alright. Okay, it's interesting. That's not that bad then. Yeah, I've got to think about this problem. And then we can like fix it. It'd be pretty easy. But in terms of performance, it's not anything to measure yet, but this is actually a bit slower. It was 0.13 for the 0.13 for the tiled version, but for 3D Froxels, it's actually slower here. And the reason why, as I said before, very simple scene. But when this thing works and we have a bigger scene, it's really going to shine. And effectively, it's going to, if stuff occludes, it will simply not try to ray trace against the stuff behind it. So there's that, at least. Rendering protein would be proper cool. I'm not sure what protein looks like, to be honest. But yeah, we're just making like basically a sphere renderer. So it's just things made out of spheres. It can animate. It can do all things. I'm even going to be doing transparency as well. It's going to be really cool. Can't wait for that. I've got some ideas. Just got to put some effort in and achieve it, you know. Built-in occlusion. Yeah, it's going to be a built-in occlusion. Although it's not going to occlude anything that's inside the same cell. Inside the same Froxel, right? So when we have a bunch of spheres in here, and we have some spheres in here, right? We obviously don't look in these. We'll still iterate over it, right? But won't be ray tracing against anything. So what we'll do is imagine if we have this ray. This ray will obviously hit this thing and this thing. But, you know, we go over this, the Froxel cells like so, check, nothing in there. We get to here. We go, okay, there's 3 spheres. There's this guy. No, I didn't hit that. There's this guy. Oh, I hit that. And there's this guy. I didn't hit that. But then after you finish this, you've got a closest hit. So what we do is we finish, because you're occluding, like there's going to be nothing closer in the Froxels past you, basically. Yeah. But I still think we could probably benefit from... Yeah, I don't know if we could actually... Because this is not a good justice of how the system works. Yeah, it's not doing it justice how the system works. Because it's actually in log2 space. Wait, do we want it in log2 space? Yeah, I'm not sure we want it in log2 space. It means the first one's going to have a distance of 1. Second one's going to have a distance of 2. Then 4, then 8. Then 16, 32, 64. Well, it's the other way around in it. It's yeah, so you have 64 of a distance in the last one, 32 there, 16 there, 8 there. So obviously it's not scaled correctly. Yeah, I got to think about it if we want it in log2 space or something else. But anyway, that's for optimizations when we deal with that. Need a first version. But yeah. So in the next stream, we'll fix this up, and then we'll probably start on doing some models. Sorry, we might do the camera work. We'll see. I've got a list on the Discord. Have a look. Is this code open source? No. I have my custom C compiler, which we use. We have a custom C compiler which compiles C to SPIR-V, and it allows you to use C as a shading language, basically. This is open source, and this is what we use. But if you want to get access to the source code for this project, you can, if you support via Twitch or via Ko-Fi, that's a much preferred method for me, because Twitch takes like a lot of the percentage. You can basically join the Discord, link up the account, and you can get access to the GitLab, and then just clone the repo and have a play and whatever with it. It works on Windows and Linux, and it works on AMD, NVIDIA. It might crash on Intel, but it should work on Intel at some point. But yeah. But yeah. You're on Mac for play, yeah. No Mac. Yeah, custom C compiler I made all by myself. Yeah, it's really cool. Writing shaders in the same source language is like something that's like not really seen, and it's like really silly how we just don't have this. But we do now, and no one cares, except for me. Okay, but anyway, that's fine. People don't have to care. But yeah, as I said on the Discord some point ago, we want to test high quality models, camera controls, right? We want to add model instances, support to everything, which includes the BVH thing we've done, right? We're keeping that obviously. And we want to add the ability to Yeah, so camera controls, we need to add transforms, model instances, and then animation, obviously, for the BVHs too. So we need to rebuild the BVHs, the bottom levels, and yeah, it's going to be cool. A lot of fun. So this is basically what's happening in the next so many streams. Gonna build a more complex level. It's gonna be amazing. We're gonna have more little things other than this guy. I'm gonna try and push the total number of spheres up pretty high. Right, I need to shoot now because I've got work tomorrow. But I'll next be on Sunday at 6 p.m. GMT. And I stream Tuesdays, Thursdays. You can check out the schedule. It's all on there. But yeah, thanks for coming, everyone. Dumbbell ship has served you well. It's going to keep serving me well. Don't worry, it's going to come. But we'll get more different ships. I'm not sure what game I'm making, but let's just make little spaceship things. That sounds fun. With SDFs. And just make them out of spheres. Be fun. Right, have a good weekend, everyone. See you all Sunday. And yeah, catch you later.